Cool. So, hi everyone, and welcome to discussion number 3. So, just to start off with some announcements. So, this Friday, both Project 2, so multi agents, and the Grayscope assignment on exam logistics are due. So, please keep that in mind. And then for this section, we are mainly just going over games and specifically like what the different types of games are and how to do pruning on the different types. Cool. So that being said, let's just dive into a quick mini lecture on games. Cool. So with games, usually there is this notion of whether a game is zero sum or not. And a zero sum game essentially just means that our gain is equal to the opponent's loss. And vice versa. So it's kind of like this really like distinct and split view that whatever we are gaining, the opponent is losing, and there's no idea of this kind of middle ground. Cool. And then with the zero sum game, you'll usually see the different values represented just as one number, and that's because you have this like, if it's our gain, then it's their loss, so you only need one value to kind of represent that. Cool. And then within game trees, you can have different types of nodes. So usually whenever you have a square node, and these are usually the leaf nodes, this is just going to be a utility node. And then if you have a upward facing triangle, that's going to be the max node. And then downward facing is min. And then if it's a circle, that's what we call a chance node. And then for chance nodes, we usually have a certain number of children for that node, and then if no like default probability is specified, then that just means that for each children it's going to be like 1 over n probability of it being that children. So if there is 3 children, then each branch is going to have a probability of 1/3, for example. And then usually there are 2 specific types of games trees that we look at, and one of those is called minimax. And that is just essentially alternating layers of max and min. And I'm just going to use their symbols since I think it's easier and quicker to write it out like that. Cool. So with this, that means that the optimal opponent is assumed. So that's why the minimum levels represent your opponent acting, because the opponent will pick the best action for them, which is therefore the worst action for you, and that represents picking the minimum value at that level. Cool. So that's why in general minimax is used to represent an optimal opponent. And then another type of tree is expected max. And this is just alternating layers of max nodes and chance nodes. And then with expected max, you're more considering the average case of how your opponent acts. So you are not considering an optimal opponent anymore. And then in general, this just kind of adds some randomness in because of the chance nodes. Cool. And then other than these 2 main types of trees, there's also just this general notion of a mixed layer types and that's just basically trees with any like mix of max, min, chance layers, and that can be in any orientation. And then with game trees, we always talk about this idea of pruning, and specifically we talk about alpha, beta pruning. And then with alpha beta pruning, what you're doing is that you're kind of looking through, and then based on the values in certain nodes, you realize that you don't have to look at some nodes. So because of that, you can just prune some nodes and then make your solution faster, because then you don't have to look at everything to determine the best solution. And just some things to kind of keep in mind, there is this formal definition of alpha being the max's best option from the current root path. And then beta is usually defined as the min's best option from the current move path. Cool. And then for kind of more details of how alpha and beta is incorporated into algorithm, I really recommend just looking at the pseudocode that is included in the lecture slides. But in general, some things to just kind of keep in mind about alpha beta pruning is that you never prune the leftmost branch. And that's because when you look from left to right, the leftmost branch is the first branch that you look at. So you don't have any kind of base values to judge based on whether you can prune yet. So that's why the leftmost branch of the tree, you always have to keep all the values. And then something else to kind of keep in mind is that with pruning, when you kind of judge whether you can prune or not, you kind of take what I like to think of as this kind of 3-layer approach. And all that means is that whenever you're deciding whether you can prune a certain element, you have to look at that layer, the layer above it, and then the layer above that. So you should always be looking kind of at 3 layers at a time, and then based on that, you can use the relationships between the layers to see whether you can prune or not. Cool. And then we are going to go into more examples of alpha beta pruning in the problem statement. So this is where I'm going to end that for now. And then, but just like another quick thing to point out is evaluation functions. And these functions essentially just estimate utility of non-terminal nodes. So essentially it will just be usually a linear combo of the different features, and it will just kind of give this like estimation of the utility for the node. And that's because sometimes you can't get all the way down, or it's not that efficient to get all the way down to the terminal node to get the exact utility. And by terminal node, I just mean the leaf of the game tree. So because of that, evaluation functions are sometimes used to simplify that calculation. Cool. So now we are done with our mini lecture, and we're just going to dive straight into problem 1. So in part A, we are given this zero-sum mini-max game tree, and you can tell because you have the max node, so the upper facing triangle on the top, and then the 3 minimum nodes in the next layer. Cool. So in part A, we just want to fill out the values for this tree. And then you can go through that and just kind of fill out the tree from Usually I just go left to right from bottom up. So for example, let me put the answers in blue so that they're more noticeable. So just out of 10, 8, and 3, the minimum is 3. This one, the minimum is 2. This one, the minimum is 4. Cool. And then, based on these, 3, 2, and 4, the maximum number is 4. So that's it for part A. You are essentially just going through and filling out the values. Cool. So now let's look at part B. So part B asks if any nodes can be pruned via alpha-beta pruning. So now let's take that approach and start looking at this tree from left to right. So as I said earlier, you cannot prune anything in the leftmost branch because you haven't determined a value yet. So if I look kind of from the maximum node, and you look here, you have to look at all 3 utility nodes, so the 10, 8, and 3, in order to determine what the actual minimum is. You can't just not look at one of the nodes yet because this is your first value. So because of that, you cannot prune anything in your left branch. So everything on your left branch stays. Cool. So now let's look at the middle branch. So something I mentioned earlier is that you kind of want to have this like 3 layers approach, which is represented here because you're kind of looking from the max node and you're taking into account the node of minimum nodes and then the utility nodes. So here you already know that if you were at your max and you looked at the leftmost branch already, you know that your currently highest value that you have is 3. So you can look here and then see that the first value is a 2. Well, you know that this middle layer is a minimum node. So that means that this node can be 2 or anything less. So it will specifically be 2 if the other 2 nodes are greater than 2, and then it will be the other node's value if one of the other nodes is less than 2. So because of that, you know that the maximum of this minimum node is just 2 already, no matter what the other 2 node values are. So because of that, you no longer need to look at the next 2 nodes because you know the maximum value that this node can be is just 2. And 3 is already greater than 2, so when you are taking the max, you know that 3 is fine already, and this middle branch is always going to give you a smaller value. So that's why you can prune those 2 nodes. Cool. So now let's kind of do a similar thing with the last or the rightmost branch. So here we look and then see a 6. And we see that, well, 6 is greater than 3. So we still have to look at the other values to see if there is a smaller value or not. So then now you move over and look at 5. You look at 5 and see that, well, 5 is still greater than 3 as well. So even if 5 is a minimum value, or you would still not be sure. So you have to look at the following value as well, which you see as 4. And then since you've looked at all of the values already, then you know that the minimum is 4, and then the max on top becomes 4 as well. So because of that, you cannot prune anything on the rightmost branch. So that's why overall in this problem, the 2 values that you can prune are the 15 and the 7. So the 2 values that I have crossed out in like a dark pink right here. Cool. So for these kind of pruning ideas, I generally just recommend like trying out different problems and thinking it through. I personally find it easier to kind of just like get the instinct of whether I still need to look at a value or not versus like running through the pseudocode of the algorithm with like alpha and beta, because I feel like that can be like kind of long, and I think the ideas are more shown via just kind of looking at the diagram and thinking through whether I need to know the next number or not versus like writing out whether I'm like updating alpha, updating beta, etc. So this is kind of like how I like to think about it, and yeah. Cool. Now let's move on to part C. which is the same tree in terms of utility nodes, but now it is expected max instead of a mini max tree. So because of that, the middle layer are now all chance nodes. Cool. So since by default, whenever you have a chance node, it will just be an equal probability among all the children. And here we have 3 children, so each branch kind of has like a 1/3 probability. So based on that, to get the chance node, we would just do 10 plus 8 plus 3 over 3. So 21 over 3, which is just going to be 7. And then here 9, 24 over 3, which will just be 8. And then 15 over 3, which will be 5. And out of these 3 values, the maximum is 8. So that will be the maximum node. And then now part D asks, which nodes, if any, can be pruned by alpha-beta pruning? So if you look at these values, we now have chance nodes, which means that each of the utility nodes are taken into account for each chance node. You're no longer just kind of picking one of the utility nodes based on whether it's the minimum or the maximum. So because of that, you cannot prune any nodes. And that is actually what ends up happening most of the time with expected max, because you always need to consider all the nodes under each chance node. So you can't prune any of them, otherwise they will like affect your chance behavior. Like for instance, if I look at the 7 node and I look at 10 and 8 and 3, then it takes into all account. I can't just stop looking after 8 and then like assume the value will be some way. So that is usually the case with expected max. There is just kind of one situation where you can prune an expected max, and that's when your nodes have an upper boundary. So for example, in some problems it may say that for all your utility nodes, the max value is only going to be 10 or something. So then you can use that max value and calculate and see, like, if you look at 2 nodes already, you know your next max node is only going to be at most 10. So if that, with using 10 as a calculation, the chance node is still lower than other ones, then you may not need to look at that node. So that is an example of when expected max can prune. So let me actually just note that down. Can only prune in expected max if have utility upper bound, because then you're usually just using that bound as your calculation points. Cool. So now we are done with problem 1, and then let's move on to problem 2, which deals with non-zero sum games. So non-zero sum games are just games where you kind of have utilities for each player, because my gain is no longer my opponent's full loss. There's kind of this middle ground now. So there is possible that some node will be beneficial to both of us. So that's why in this tree here, you see that there are 2 values per each node, and that's why for the first value it represents player A's utility, while the second value represents player B. And usually with non-zero sum games, this is just how it's represented, with the 2 values, or essentially 1 value per player within each node. So it is possible that you even have like 3 values per node, and that just symbolizes 3 players. But in general, you still fill out this table in the same way. You just kind of like fill it out twice, and you look at all the player A values and then look at all the player B values. So to fill it out in part A, I would just look through and see, well, this is a max node. So you have 10, 8, and 3. The maximum is 10. for player A, and you have 1, 3, and 5 for player B, so the maximum is 5. And 2, 15, 7, so 15, 4, 9, 8, 9. And then here you're 6, 5, 4, so 6, 5, 10, 12, and 12. And here the maximum is 15 for player 1 and 12 for player 2. And something to notice is that like with non-zero sum games, you kind of just have maximum nodes in general, because as a player, you're always trying to win, and to win you need to maximize your utility. So since the utilities are now represented separately for each player, for both players, you just constantly want to maximize utility, which is why you can just have maximum nodes. Of course, sometimes non-zero sum games may also introduce kind of minimum or chance nodes to kind of add some randomness to the game, or to kind of add like a setback to the game. But if it's just a non-zero sum game, a normal one with no kind of like other factors, then in general people just want to keep maximizing their score, which is why both of these layers are max nodes. Cool. And then part B now asks the question of pruning. So it asks if any of the nodes can be pruned. And similar to the expected max situation, the answer is also none. Can't be pruned. And that is because with non-zero sum games, there can be some node in the tree, specifically some leaf node, that is both good for player A and for player B. So when you are looking through, you don't know whether there's another value that is good enough. So you have to look at everything in order to be sure. And a way to kind of also see why mechanically alpha beta pruning no longer works is that earlier we kind of had these alternating layers of minimum nodes and maximum nodes. So we know like a cutoff based on the previous nodes. But now, since that they're all maximum, you no longer kind of have this like reversing between minimum and maximum. And because of that, you always want to keep looking just until you find the maximum. So in every single layer, you are essentially just looking for the maximum. And in order to be sure you have the maximum, then you have to look through everything, because there can always be a potential number that is bigger. So that's why in non-zero sum games, you cannot prune. And yes, so that is it for this week. In general, this worksheet was pretty short and pretty straightforward. I think in general with games, you just want to be able to like fill out the game tree and then be able to determine which nodes can be pruned. And then sometimes there are also some questions where they tell you the specific node can be pruned and ask you kind of in a reverse way what the boundaries of the values for that nodes, and you essentially just want to go back and kind of write out the values that the nodes can be between, and then determine like if it is in this range, whether that means it can be pruned or that means it cannot be pruned. So yeah, so in general for games, I would really recommend just getting used to the whole idea of alpha beta pruning, and then run through a lot of examples in that so that you kind of understand it going like forward and going in reverse, as I mentioned with that example. But cool, yes, otherwise that is it. And yeah, this week's section is pretty short, but I hope you enjoy games.